mass. Yes. All right. So, static. I'll pull this down for the time being so you can see that. When objects are in static equilibrium, the biggest thing I want you guys to take away, torque, all the torque is going to be equal to 0. The net torque, I should say, it's going to be 0. The net force is 0. That's it. That's what I want you to know. The net torque, the net force, all going to be equal to 0. Okay? Oh, that's nice. Not 100%. Stats right there. Okay. All right, so some tips. You can mathematically put the axis of rotation anywhere you want. However, it is pretty good to put it on a spot where you don't know what the force is.
Oh man, trusses. Jake, trusses. Not again.
They're easy though.
Yes, I know they're easy. Moments.
Do I have a question, Cole?
I can wait.
Wait, until when? Future?
Yeah.
What if you forget though?
I was thinking 2 dumb questions in a row might not be play.
Just do it.
There are no
Yeah. Well, I mean, I got the time.
Okay, what's your opinion on like the sound of rain?
The sound of rain?
You enjoy it or like you one of those?
Well, I'm trying to like physics here.
I like the smell of just
Makes
rain.
me go time.
I like the smell of rain.
I like this. I like white sound, so yeah.
You like the smell.
I like this.
The smell's the best.
I'm indifferent on the smell.
The smell?
Yeah.
All right.
It smells like concrete.
It smells horrible. Smell of rain.
The soil.
All right.
It smells like concrete.
So let's first try. First try. You guys see that? Of about an inch.
Yeah. It's pretty good at their shoes.
All right. So let's check this out. A child with a mass of 43 kilograms is supported on a plank that is 10 meters long. Okay, well, let's start there. So the mass of the kid is 43 kilograms. Okay, mass of the kid is 43 kilograms. The plank is 10 meters. So what is it from this to the kid? 7.5 meters. Let's write that. And what's the distance from here to here?
He is very dense.
2.5.
Okay.
That little guy is 90 feet.
Does it make sense where I got those numbers? Okay. So we got the kid. Now, the plank's mass is negligible. I always struggle with that word. Negligible. Cool word. What? We're just going to ignore the mass of the plank. All right. So when we ignore that, who exert the forces F1 and F2 as indicated? Find the forces required to keep the plank in static equilibrium. Okay. So looking at this problem, we can put the axis point anywhere we want. Where should we put it?
On the kid. No, wait. Whoa. I'm down.
Maybe not.
I'm lost.
Maybe you can put it here.
Onto
I saw a hazard how to never let your markers run out.
What?
So what you do is when one runs out, you go to the teacher's room just switch it for one of theirs.
That's pretty good.
Yeah, but he has a whole thing of markers.
Yeah,
he
he's got
has,
like a
like,
treasure trove.
I think I'm good on markers. I like the strategy though.
Just that way
Oh,
you
that
never,
was
if you
nice.
never run out.
That's good. That's good.
That's a good marker.
So, if we look on the torque that she's providing, how much total torque is she providing right here? Whoa! You're exactly correct. That was pretty easy. Why? Why 0?
Oh, it's just a-
My radius is 0. Very good. So torque is equal to force times my radius times my sine of theta. Okay. My radius is 0. So she is providing a torque of 0. Pretty easy, right? We like that one. Let's look at the baby. Or the kid.
That's a 95 baby?
You haven't seen a 95-pound baby?
I have not.
Picture.
I weigh 95 pounds.
Right there's a picture. All right, so let's find the torque of the babe. We're gonna call him baby. Should I say child? Torque 2? What? I'm saying torque baby. All right. So my equation is force r sine theta. How do I find the force of the baby?
Mass times acceleration.
Mass times acceleration. All right. So mass 43 times 9.8. My radius is 7.5. What's sine of theta? Ooh, this really smells.
I love that smell.
90. Very good.
The smell of a marker.
It's actually like same like I think it's the same kind of thing that like you would get high on.
It is.
Yeah.
We used to do like some of the smelling markers.
In kindergarten.
So how much? What number did you guys get? Guys, it's not.
Wait. So the
Is that what you guys all got?
so the
Okay.
degree is 90, right?
Yep.
And so it's just one sign. It's just
Okay. So we got that. Now, the key with statics is my torque, my net torque has to equal 0. Well, I have 0 here. I have 3,160.5 Newton meters going down, which means this guy has to have 3,160.5 Newton meters going up. So that's his amount of torque.
would the kids be mad?
If, in theory, it would be negative. Because if you think about it, going down.
It was a question. You just said no questions are dumb.
Okay?
No, you insulted me.
Okay. So when the question says find the forces, let's find the forces. Okay, so we know the guy's torque over here. Torque is equal to force times my radius. What's his radius?
Hey, that's offensive.
Times the sine of theta. Okay. So this one's pretty easy.
Physics Jake, okay, I don't need this.
That one's pretty easy, right? Basically just gotta divide 2 of 10 over. Is this a good question?
Yeah, so what would happen if we would have put the axis on force 2?
Then
Axis.
this would have been 0 radius, and we would have done the exact same thing to this side.
Okay.
So there's just different answers for where you put the axis.
Would it be the same?
I mean, it'd be the same answer, but it'd be force 1 instead of force 2.
Right.
Yeah.
Okay.
Alright.
Yeah, I mean, you could have put it on either one. The reason you wouldn't put it on the baby is because we already know that force.
So
Right.
is it perfectly correct to say that one of them has 0 force and the other has, you could make an argument for either one having 0 force?
0 torque.
The force is still
Okay.
0 torque.
So then how do we find the torque of the other one?
How do we find the torque of the other one?
Force of the other one, sorry.
The force of the other one. So, well, we know it's torque. So 0, 4, well, actually, no, I got it. It took me a second.
You just have to read the process.
Well, the net force is 0 as well. Yeah.
All right. So if you look at all our forces, so we're gonna have force 1, force 2, force baby,
Force baby.
all has to equal 0. Okay? All has to equal 0.
Has this now shifted like a linear? We're just going up and down.
Okay. So force 1, we don't know. Force 2 was 316. That's what that equals. 36. Oh, force baby is 316. I assume that's what you said.
360 is force 2.
What's the force of the baby?
Whatever, 43 times 9.8.
421.
Minus.
Yeah, negative
1 to be negative.
Okay. Yep, that's going down. Very good. So force 1 is equal to 105.
Yes.
Let's check.
Good.
That is correct. That is correct.
Okay, I don't know if this question has already been asked, but okay. If you put the axis on the man, would the torque of the baby be the same or would it be different since the radius is different? Like, how can there be like 2 different torques? I guess is my question.
Hold on.
Wait.
Whoa. Wait a second.
So the best answer I got for that is if you look at, let's say I have a large wrench.
What?
A wrench.
Okay.
And that's going to be a hard example. We're talking still about the baby, okay? The baby's here. This person is going to have a lot more torque, right? It's going to be easier for this person to hold it than this person, right? So depending on who you're looking at, if you're looking at this person right here, this person's going to have more force required to lift the baby than this person, okay? So yes, when we're talking about this person, this kid's torque is going to be greater compared to this person since he's a lot closer. Where if we're considering this person, our point of view, the baby's going to have a lot less torque. So it just depends on the point of view. So when you're looking at it this way, I don't have that much torque. The baby doesn't affect me that much. But when you're on this side, the baby's actually affected me a lot. So the torque of the baby actually changes. It just depends on how you're viewing it, which person you're viewing it
So
as.
it can change?
It can
on
change.
what the axis points?
Correct.
Did you make that up as you went along? Because you seemed very confused at first.
At first.
Yeah.
But then it like light bulbed in my head.
Process like what you're asking.
That was a good question. Yes.
So can you not solve the problem if you were to put the axis on the baby?
Oh,
Oh.
if you put the axis on the baby,
There would be no way of determining.
so R would be 0. So torque would be 0.
We wouldn't know their weight. So.
Yeah, you would not. Unless, I can't think of a way. Unless you would have one of the other forces, I don't think there would be a way. That's a good question. That's a good question. Let's try one more and then I got it. Got a tough one. Got a cat. Who doesn't like cats?
I'm allergic.
I'm actually allergic too, so.
I still have one, bro.
Do you really?
Yeah.
All
My
right.
friend has a cat, and
An
it's
outdoor
his
cat
Goldie.
later or a
The first
indoor
time I
cat?
met it, it scratched me in the face. I just don't like it.
Here we
It
go.
don't like me, so.
There's that like eating thing that if they like you, it's
See, and then she like puts up my gloves on my freaking.
so I threw it off.
Okay. So once again, our torque, our net torque has to be equal to 0. Our force net has to be equal to 0. So let's see. A cat walks along a uniform plank that is 4 meters long and has a mass of 7 kilograms. Okay. Okay. Let's see. The plank is supported by 2 sawhorses. One is 0.44 from the left. Okay. Left of the board, and the other is 1.5 meters from its right end. So this is 1.5 meters. Yeah.
Yes.
Oh,
Yeah.
I did.
Yeah.
What is the mass of the cat? That's what we're trying to solve.
Yeah.
So the plank, I'm going to put this down here.
I was.
Wow. That's why I was just making sure you guys were paying attention.
Yeah. Yeah.
Tommy gets the 10 extra credit points.
I'm very sorry.
All right. Thank you. Thank you. All right. Let's see. 1.5 meters from its right end. And the cat reaches the right end, of the plank, beans to the tip. What is the mass of the cat? Okay, so we're trying to find the mass of the cat. Okay, so now we have 3 different torques involved. Okay, so let's find. Oh,
That's an amazing cat.
that is an amazing cat.
I just really can't.
Let's put. Our center there. Okay, let's put our center there. Okay.
Wait, would that make force 1 not 0 then?
Force 1's still 0. Okay. So we got to find torque 1 there. We got to find torque 2 there. We got to find torque 3.
Wait,
Yeah.
how do we know where to do the 7 kilograms?
Say what?
How do we know where to do the 7 kilograms?
Center of mass, center of the board.
Well, how do we find that?
The entire board was 4 meters long. So halfway here to here would be 2 meters long. Right? That would be 2 meters. So here to here was 1.5. So what would that be? 0.5. So from our center would be 0.5. Or from our axis point, from our rotation axis point, our center of the board is 0.5.
Are we ever gonna get a question that's asking like something where the center of mass is moving, or is it always just gonna be like intermediate?
Ooh.
I just remember-
It's always going to be instantaneous. Yeah. That's a good question.
I have a question.
Question.
Okay, will you ever have a question on like a quiz or test where it makes us find the torque from 2 different axis points?
Yes.
I was just,
Did that last question ask for torque from 2 different axis points?
yeah, but I don't know. I was just like with the last one, I was like considering like you do it from like the woman's point of view and then like do another step from like the man's point of view. So then you find like 2 different. You see what I'm trying to say?
Are you? So like,
Do that?
say what?
Did we already do that?
Are you saying like, let's say Landon and I are trying to lift the desk together, but we're on the same side?
No, like, so, you know how we solved from the axis point of the woman?
Woman, yeah.
Would we ever have to solve from like the axis point of the woman and then like of also the man?
So two different axes.
Yes.
Ooh, no, I don't think so.
Okay.
Because wouldn't it be just like whatever we found for the man? We just switch it, right?
Pretty much.
But then you gotta change what that organ to the base.
Yeah. I see what you're saying. All right, so let's do this. Torque 1 is equal to,
Wait, no, wrong one. I was thinking of torque 1 was by force 1. Never mind.
I was like, oh no. All right, so we got
I'm out of it today.
force, radius, sine of theta. Okay. So the force is mass times gravity. So 7 times 9.8. Radius is 0.5. My bad. Sine of theta is just 1. So what is torque 1? 34.3. Okay, that's Newton meters. Perfect. Torque 2, easy one. What's torque 2? 0. Why?
Because
It's the axis point. So torque 3, so torque, remember, torque 1, torque 2, torque 3 all have to equal 0. So,
wait, wouldn't? So torque 1, would that be negative because the direct or the distance is to the left of it, to the left of the axis point? Because in order to get a net of 0, they're always one's gonna have to be negative. Don't they?
in theory, yeah. So, really, this number's going down. So, we can put a negative. Okay. Yeah, we can do that. All right. So if we look at torque 1, 34.3 plus 0 plus torque 3 equals 0. What's torque 3? 3 is equal to the force R sine theta. Okay. So when we 34.3 is equal to the mass times gravity of the cat times R. What's R going to be? Yep. Times sine of theta.
Why is it 1.5?
Because it's 1.5 from the right hand. So here's the sawhorse. Here to here is 1.5.
Isn't the cat over torque 3?
Yeah.
So wouldn't it-
Well, we're pretending the cat's right here.
Okay.
Great question. Great question. Okay. What you guys get for the mass? About 2.3.
Would we include the mass of the plank in that instance?
No.
I got 2.3.
Yeah.
Why would we not include the mass of the plank if it's like, if we're including the mass of the plank everywhere else, the cat is still standing on the plank?
Well,
So we included the mass of the plank when calculating torque 1. So torque 1 right here, this was the mass of the plank. So that gave us torque 1. Torque 2 was 0. Torque 3, well, we know our net has to equal 0. So we considered the mass of the plank right there. So when considering torque 3, we're just focusing on the cat. And what the mass of the cat is. Yes.
So, in the middle of the plank, that's the only place where the mass applies.
That will be the center of mass, yes.
Okay, so.
All right.
That makes sense, but.
My last question I want you guys to do on your own. Is this?
What?
That's the challenge question.
This is my challenge question.
I thought that was the chat.
The answer's three, I already know it. It's got three.
Okay, so you got to remember torque and net force is equal to 0. Okay?
Oh my god.
What I want you guys to do is solve for mass 1 of the milk, mass 2 of the broccoli, and mass 3 of the bread.
Oh. I'm gonna.
It's only this much work.
Only.
Oh,
We have no time, we have 10 minutes, I don't know if that's.
we have
Maybe
8
we'll do it
minutes.
at like the end of the year for fun.
This is the end of the year.
Oh my gosh, it is.
We're in
Don't
quarter
say
4.
that, don't say that. This is my last quarter ever.
Okay, I won't say it's the last quarter.
We have
It's the last
semesters in
few
college.
months.
What? 7 others weren't enough for you?
What?
7 others weren't enough for you. I'm ready to leave.
I just,
I'm so
Question.
okay, is it like, does it look really complicated, but it's really easy and it should only require 2 steps, or do we have to find torque for like every single thing going
I mean,
Yes.
you're eventually gonna have to set. So these two torques are gonna be the same, right? You're gonna have to equal each other. But not knowing a mass, we're gonna have to solve for one of them and then plug it into the torque that equals out the meat.
I'm gonna say that before.
Okay.